My name is Tony Baker and I'm head of the School of Chemistry and Forensic Science at UTS. So what we're doing today is working on some fairly simple chemical reactions. Often a chemical reaction can take place without there being any really obvious sign, but in these particular reactions we will see things happen. Precipitates will form, gases will bubble out of a solution. So it's some of the clearest ways in which you can actually see chemistry happening.
We're doing an experiment where we're given a set of solubility rules and asked to determine a series of unknown samples based on reacting them together and looking at the products, and then observing what we saw and going back and looking at those solubility rules and determining what those unknowns were.
We approached it systematically and used the first solution to test with all the remaining ones, the second one with everyone but the first one, and so on until we'd reacted the 5 together, which then allowed us to record results and then systematically identify each one.
It was interesting because it's very similar to a prac that we're required to do in the HSC chemistry course, but took it from a very different perspective. So my approach was to determine which reactions could be carried out, and then to try and determine which was the least reactions that we'd need to carry out in order to get a result. And so just looking at the different combinations, and then as we're going, reflecting on the results that we got to see if we could narrow it down.
I think the most engaging part for the students would be that I haven't told them the answer, that they have been given a problem and they can be competitive about finding a solution. The challenging part for my students, in my experience, would be them understanding and reading the solubility tables. They'll have to have a decent understanding of the chemistry involved in order to complete this experiment successfully.
And the next component of it, which I've included into the session as well, is to actually design a set of 5 solutions of which they could give to their classes and have them do the same problem. So it's actually that extension beyond the actual practical and the problem they're faced with, to be able to design a problem to actually give their solution, their students.
So the extension component, where students are required to design their own set of rules, if you like, in terms of being given the solutions, is the difficult bit, and that's the bit that really requires the higher order thinking and shows that they've understood what the solubility rules are and what they mean in terms of real world science. And I guess that's where I think the interest lies with the kids, that it does have applications to the real world.
The aspect of the science syllabus that this best address is chemical reactions in stage 5. It possibly also relates to stage 6 chemistry.
This experiment is easily reproduced in a high school across the state. The chemicals that we used were readily available in schools. Didn't use anything more than beakers, test tubes to do, easily reproduced in school.
Well, one of the main points is that you can see chemical reactions take place. I would argue that that's a principal aim, and it's very important to be able to demonstrate that to students in a fairly simple way. But that in itself is not enough. I think we want to be able to pose problems that students will have to determine a strategy to actually solve that problem. They'll actually have to propose a way that they're going to actually work out what each of the solutions is, and indeed use some information to actually predict whether there'll be a reaction or not. Because that's really where science is working for you. It's not just that you're doing experiments and making observations. The real power of science is you can make predictions. And that's where we're really wanting to get to with this.